So in the January lecture series, if you went to my lecture series in January, I demonstrated how we differentiate inverse trigonometric results. So just recall that when we differentiate inverse sine, we get 1 over root 1 minus x squared. And when we differentiate inverse cosine, we get negative 1 over root 1 minus x squared. And when we differentiate inverse tan, we get 1 over 1 plus x squared. So we also looked at the special results when we got x over a instead of just a regular x. So remember that when we differentiate inverse sine x over a, we get 1 over root a squared minus x squared. And that when we differentiate inverse tan x over a, we get a over a plus x squared. Oh, this should be a squared here. So it'll be a over a squared plus x squared. So don't forget there's an a in top. Well, this one doesn't have an a. So don't forget the squared here. Okay, so now that we know how to differentiate, we can go the other direction and we can, once we know how to differentiate, we could go the other direction and we can integrate. So now we can say that the integral of 1 over root a squared minus x squared, that's just going to be inverse sine x over a plus c. And when we integrate a over a squared plus x squared, we'll get inverse tan x over a plus c. And these are the standard integrals, but you can go a further step and you can actually remember the reverse chain rule. So if you have a function inside the function, so instead of x, if we had a function here instead, you want to make sure that the derivative of that function, so if this was a function instead, we want to make sure that the derivative of the function is on the outside before we can then integrate the entire thing. So that's actually what appears on your reference sheet. So if you're curious about why your reference sheet wrote it like that, it's because they also incorporated the reverse chain rule into your reference sheet. So here, you get inverse sine. Here, Nessa for some reason likes to divide both sides by a. So here what actually happens is once you divide that by a, this will go away. So you just get 1 over a squared plus x squared. You get that result. I'm not really a big fan of that form. I just like this normal form here to get inverse tan x over a. But it's literally the same thing. It's just what happens if you divided both sides by an a. So same result. So if you have a function inside, you want to make sure you are multiplying by the derivative of the function inside before you can integrate. So here's an example of an integral that involves inverse trig. So we got 5 over root 9 minus 16 x squared. So how do we integrate it? Well, notice that we can write 16x squared as, so here 16x squared is just 4x, the entire thing squared. So here we've got a function inside. Instead of having a regular x squared, we just got a 4x squared now. So also this 9 is going to be 30 squared. So here we've got a function inside. Remember our form that we know how to integrate is 1 over root a squared minus x squared. We know that when we integrate this, it will become inverse sine x over a plus c. So here, but we have a function inside instead of x. So the derivative of 4x is going to be 4. So I want to make sure I have a 4 on being multiplied already. So I could take out this 5. So if I want a 4 up there, dx. I can't just add a 4. I need to balance it out. So I'm going to divide by 4 in the front. So I'm not changing the question. I'm just simply adding 4 then divided by 4 so that they cancel out. So now this is in the perfect form on what you have on your reference sheet, where you got the derivative on the outside and you got a squared minus f of x. This is like x squared. So this will simply become 5 over 4 inverse sine 4x over 3 plus c. And that's how you do an integral like that. Just remember, if there's a function aside, you want to make sure that the derivative of the function is already on the outside. In this case, we made sure that the 4x, the derivative of 4x is 4. That's on the outside. And then I can integrate it like normal using our result for differentiating integrals like that in this particular form. Okay, in the January lecture, I also talked about how to integrate sine squared x and cosine squared x. And I mentioned previously that in order to do that, we need to use the double angle formulas that we have for cosine. So basically, what happens is, remember with cos 2x, you can either write that as cos squared x minus sine squared, which you can then further simplify. You could further manipulate using the Pythagorean trig identity as 2 cos squared x minus 1 or 1 minus 2 sine squared x. Now, you can then make cos squared x a subject or sine squared x a subject and you get results. But remember, when you're integrating, you can also, the double angle formula applies. It doesn't need to be a 2x as long as you just make sure that the angle you get when you apply the double angle formula is half of what you had originally. So, for example, if you had cos 6x, that's still the same thing as 2 cos squared 3x minus 1, so long as the angle is half of that. So basically, when you when you have nx, when you rearrange it into this form, you just have to make sure that that's just double what you started with. When you make this a subject, for example, if we were trying to integrate cos squared 3x, this will still be half 1 plus cos 6x, and we'll just have to change that into this because this thing is much easier to integrate compared to that. So just like I said, it comes from your cosine double angle formulas, which you learned in year 11, like that as expressed, and when you rearrange it, you can get these results. So luckily for you guys, these results are on your formula sheet, but it's still useful to know where they come from, because in the old syllabus, when I did my HSC, we basically weren't given these formulas on our reference sheet. We had to rearrange them from the double angle formula. So we had to know them by heart, otherwise we would be sort of screwed in an exam if we didn't know what the process was in order to integrate sine squared and cos squared. So here's a question. Let's say we wanted to integrate 2 cos squared 4x. Well, this thing is, if we take out the 2, we know that when we say cos squared x, when we get cos squared nx, that's going to be half 1 plus cos 2nx from the double angle formula. So this is going to be half, we're going to change the cos squared 4x into half 1 plus cos. And remember, it just has to be double what that angle is because it came from the double angle formula. So it will be 1 plus cos 8x with respect to x, like that. So now the 2 and the halves cancel out. So we're just left with integrating 1 plus cos 8x, like that. And remember, this is a trig function, but inside the function, we actually have a function inside the function. So we want to make sure we are accounting for the reverse chain rule. So the derivative of 8x is 8. So I want to make sure that I have an 8 already multiplied on the outside before I can proceed to integrate. But I can't just randomly add an 8, I need to balance it out. So I'm going to divide by 8 as well at the same time. So here I haven't changed the question. 1 over 8 times 8 cos 8x is just going to be cos 8x. But now this entire thing, when I integrate, will become sine 8x. Because the integral of cos is sine. So when I integrate, this will be x. This will have a 1 over 8. And this entire thing here will become sine 8x. And it's an indefinite integral. So I want to make sure I do a plus c. So you can see my final answer here is going to be x plus 1 over 8 sine 8x plus c. And that's how we integrate results with sine squared x or cosine squared x. So here's another question. The derivative of a function is given. This is from the 2010 HSC paper. We're told that the derivative of a function f of x is given by f dash of x equals sine squared x. And find f of x given that f of 0 is equal to 2. So we're told the derivative, but we're asked to find the original function. So you can, of course, pause this video and attempt this question yourself, or or you could continue watching and where we'll be going through it. So if we're told what the derivative is, which in this case is going to be f dash of x, which is going to be sine squared x, that's the derivative, we can say that the original function is what we're going to get when we integrate the derivative. Because remember, integration is the reverse of differentiation. So in order to integrate sine squared x, I'm going to apply a rearrangement of the cosine double angle formula. In this case, it's going to be 1 minus cos 2x. And here, I want to make sure the derivative of 2x is 2. So I want to make sure I have a 2 on the front, but I don't want to change the question, so I'm going to divide by 2 as well. So this will become half x minus half sine 2x. Because this entire thing becomes the sine 2x. So this is going to be equal to half x minus a quarter sine 2x plus c, because it's an indefinite integral. But the thing is, we want to find the function because we're given extra information that when x equals 0, the function is equal to 2. So we could use this information to help us find what c is. So when f of 0 is equal to 0 minus quarter sine 0 plus c, and that's equal to 2. So sine 0 is just 0, so we know here that c is equal to 2. So therefore, our final answer for f of x is that it's equal to half x minus a quarter sine 2x plus 2. So that is our final answer for this question.